morning, everyone. So let's get started. So maybe first of all, please introduce jurors to all of you. So I'm stage1 from National Taiwan Normal University. I serve as chair in this session, and then Professor Hong Ying and Professor Li Yinren and Professor Lin Wenqing and Professor Lin Laoshi.
Thank you.
Okay, and then I would ask all the captains to briefly introduce your team. From our reporter.
Good morning. I'm the captain from Team Mingdao Meiyan, and we are from the Mingdao High School. And this is Roger, and this is Shou, and this is Michael, this is Alan, and this is YC.
And from opponent.
I'm the captain for all niners from Taipei American School. My name is Hao Ting. This is Lorraine Yu, student CEO, Stephen Peng, and Daniel Lee.
And review.
Hello everyone. I'm the leader of the Level 2 from Gangwon Senior High School. I'm Wu Youshen. This is Wu Yizhen, Hong Luojia, Yan Longzhi, Wu Yujing. Thank you.
Okay, so let's start this fight. And first of all, the opponent has 1 minute to challenge the forward.
We challenge the reporter to topic 6 from written content.
We are set.
Okay. Number six, right? Topic number 6?
Yeah.
Okay, number 6 is accepted. So each team should have a representative and write your name on the blackboard, please. Okay, so the problem number 6 is accepted, and then report that you have 5 minutes to prepare. So reporter, you have up to 12 minutes to present your result.
Okay, so good morning, honorable judges and fellow contestants. This is the reporter YC from Middle High School. Today I'm here to present you with 26 driven faucets. So this is my outline, and here is my closing statement. A liquid faucet develops interesting driven patterns with time between drops and on the water flow rate. Investigate this phenomenon and study how it depends on relevant parameters. So our main focuses are the driven patterns and the time between drops. And this is my demonstration video. So as you can see in the video, the shape, the pattern of the droplets and the time between droplets are slightly different as the time proceeds. So our presentation will be focusing on navigating how water flow rates affects the pattern of the droplets and the time between droplets. And let's move on to our theory. So let's talk about the shape of the droplet first. So this is a graph that we get from the paper down below that we read from, showing the relationship between the lower H position and the value of the drops. So the solid line here represents the stable stationary state, where the red dots here represent the maximum stable center impedance drop. So once the water value exceeds this critical value here, the VC here, the droplet will drops. And above it is the dotted line representing the unstable state. And since that red dot represents the maximum stable stationary impedance drops, so those patterns on the dotted line only appears in motion. And we define the dropping condition as when the gravity is larger than the surface tension. And we define the breaking point as when as the thinnest part of the water body here, because it has the smallest surface tension. And let's talk about the motion after drops. So after the droplets falls apart, there will be a remaining water up here, and it will have a surface tension pulling up, and it will try to reach an equilibrium with the viscosity, and therefore will cause a damping oscillation. And when at low flow rates, the impact of oscillation will gradually vanish, and it will go back to the solid line we mentioned here. But at high flow rates, the impact of oscillation will remain, and it will go back to the solid line we mentioned earlier here. And this is a video that you can see from here. The oscillation is already reached its equilibrium before another droplet drops. But when at high flow rates, the damping oscillation is yet to reach its equilibrium, but another droplet is already falling. And this is, again, according to the paper we read, this is the so-called chaotic phase. So, and let's talk about the chaotic system. And there are 3 definitions of the chaotic system, and we'll be focusing on the first one, sensitive to initial condition, because it's observable in physics system, and the rest of it are only usually discussed in math. And as the paper suggests, we should see a bifurcation diagram just like this one if the system is chaotic. So we further break down the bifurcation diagram like this. So it shows the relationship between the flow rate and the interval, and it has a critical value to separate the whole graph into 2 systems, which is the linear system and the nonlinear system. And we use the Navier-Stokes equation to describe the motion of the fluid. So this is the resulting body flows of the fluid. So we have the density times the local acceleration plus the convective acceleration will equals to the force caused by the pressure difference, viscosity, gravity, and surface tension. And as you can see, the second term, convective acceleration, is a projected term, so which making it when it's not 0, when it's not equal to 0, the system will become nonlinear. And about this nonlinear term, when it's not equal to 0, the velocity will vary with the system, which means that we have a convection acceleration going backwards. But when it is close to 0, the convection wouldn't affect the whole velocity, so the velocity doesn't vary with position. And let's move on to my experiments. And this is my setup. So first of all, I have a bucket with adjustable faucets, so that I can achieve different kind of water flow rates. And so I open up the faucet at a certain time, and I collect the water amount in maybe 30 seconds. And I further put it into an electronical scale to get a net weight of the water that I further divide it with my experience time, so then I can get my flow rates. And about the interval tracking, I use the film in slow motion, and I record a video, and I put it into tracker to get an exact time interval. And this is how I calculate my water flow rates. So I got the net weight of the water that I collect in 30 seconds, and I divide it with my the fixed period, 30 seconds, then I can get my flow rates. And about the determination of the faucet radius, so we tried 3 kinds of radius. So let's talk about the first one. when the radius is way large, the water doesn't fill the whole faucet, so making it unpredictable, and it does not fulfill what the purpose stated. And when the radius is way small, since the surface tension applying area is really small, so it is hard for us to observe various phenomena. So we choose the one that has similar radius with the droplets. So let's move on to my experiment 1. My independent variable is the water flow rate, and my dependent variable is the pattern of the droplets. So you can see here at low flow rates, the pattern of droplets should be the same flow rate, since the damping oscillation I mentioned earlier, it has already reached its equilibrium, so it wouldn't cause any effects to the pattern and the interval. At high flow rates, as I suggested, the damping oscillation is still on the go, so the pattern of the droplet will be chaotic, and it will not be the same. And about this, although the first drop and the second drop look similar, but once there is a slight difference, it could bring about the variation of the next drop. So this corresponds to the chaotic system definition I mentioned earlier, that's sensitive to the initial condition. When there's a slight difference, like you can see, although the water volume is similar, the shape of it is slightly different, so it will cause the difference at the next drop. And let's talk about my experiment 2. My independent variable is still water flow rate, and my dependent variable is the interval between drops. And this is my data. So first of all, in this line, you can see that the interval decreases as once the flow rate increases. And if we look closer to this part, we can see a clear bifurcation here, just like the bifurcation diagram suggested. And so at this certain flow rates, we can have it could correspond to several intervals, and just like the data we shown on your right. And so, as the paper suggested, this is the so-called chaotic phase. And we do the comparison between our experimental data and the bifurcation diagram from the paper. So we have a critical value which is around 0.3 here, and several line is between 0.2 to 0.3 gram per second. And to separate my diagram into the linear system and the linear system. And let's move on to my discussion part. So as you can see, at this flow rate, it could correspond to two certain time interval. So this is my data after checking on your right here, and this is the video showing that. So you can see that there's like two certain pattern and two certain time interval, and we further assured our assumption on right through the checker. And let's talk about the oscillation period at low flow rates. So we use checker to get the oscillation period of the damping oscillation. So we can see that at 0.2 seconds, the damping oscillation will reach its equilibrium, and further on, the droplet will fall as we define the downward direction is positive. So that's when it goes right up, the droplet falls. So we got the damping oscillation period is around 0.2 seconds, and with that, and so we can see that the dripping interval is larger than the damping oscillation period. So which means that the oscillation already reaches equilibrium before the droplet drops. So proving that the oscillation doesn't affect the water dropping interval and pattern, and we define it as periodic phase. And this is my conclusion for experiment 1. The patterns of droplets tend to be the same at low flow rate since the balanced damping oscillation, and the pattern of the droplets tend to be different at high flow rates since due to the unbalanced damping oscillation, and the pattern of the droplet in chaotic phase is in relation to the pattern of the former droplets, just as I mentioned in the chaotic system definition, that it is sensitive to initial condition. And about my conclusion of experiment 2, that interval decreases as the flow rate increases. And in chaotic phase, at a certain flow rate, there could be several corresponding intervals. And we have a critical value, it's between 0.2 to to 0.3 grams per second, and it marks the transition from linear system to nonlinear system. And based on the linearity of the entire system, we can further classify the driven states into periodic, double drift, and chaotic. And this is my report. Thank you for listening.
Okay. So now there's a time for a question of the opponent to the reporter and answer from the reporter.
Okay, so can you go back to your video slide? Video, please, presentation. Yeah. This one? Yeah. What is the red or black stuff I see on the water droplets? Is that?
Sorry?
Did you put color on the water droplets?
Oh yes, it's only for demonstrating. But in our experiment, we used pure water, so we don't have to think about discuss it.
Okay, moving on. How do you account for the secondary drops with faucet with similar radius? Can you show a video?
Video?
Yeah. What do you not have?
You mean this one?
No, for the different radiuses.
Or yeah, oh, sure. So yeah, this one.
Okay. Okay. My question is, how do you account for the secondary drops with the faucet with similar radius? You're talking about, okay, I'm not talking about the big one.
Yeah.
Just talking about the two ones, right? Like the two right ones.
Yep.
Okay. Why do you not account for the? Just move on to, okay. Let's just skip the question. Let's move on to the next question. Can you go on to slide 21?
Slide, sure. Okay.
Okay, wait. So just to clarify, what are the axes? I just can't see.
Oh, sorry. This is
Sorry.
x-axis is flow rate, and the y-axis is an interval.
Okay. 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 Can you explain where the first and second bifurcation are?
Okay. So first, the first bifurcation is off from the double jump here. So it has a small bifurcation here, and it kind of going back and to some point like it close again, and it starts to bifurcate again as a
Time's up. Hold on, 3 minutes to teaching. the next stage. The opponent up to 4 minutes.
So, hello, my name is Sumin, and I am the opponent for Taipei American School or all Nighters. So, first, the opponent's ideal structure of investigation should have been like this, and they kind of went with my ideal flow, which was to identify assumptions, compare drop rate and recovery rates, find a relationship and determine critical points, and this first possible error. But they kind of missed out on the error parts and assumption parts. Moving on to their structure. They went on with their theory, they explained oscillation and chaos, and they showed experiment 1 and 2. They talked about radius and interval, and they discussed the linear nonlinear patterns and the chaotic phase, where everything, the outcomes are very sensitive to the initial conditions. Okay, so let's move on to pros and cons. Pros was very well organized, clear demonstration, and they had a clear graph demonstrating like a theoretical relationship. But for the cons, they were very vague in the procedure, as in like they did not explain many aspects that could have led to possible errors. They also lack some variables or clarity onto those variables, and the graph was a bit unclear in that those axes, I can't really see it from here. And they also lacked some error analysis. And some additional comments would be that it would have been better if they were to have more emphasis on error analysis, because especially as they are dealing with chaos, the initial conditions matter really much, but then they don't really touch upon those possible errors or the assumptions they made on those initial conditions, because it is quite experimentally impossible to have the exact initial conditions for every trial. And I don't even know if they did multiple trials. And my points of discussion would be as follows. Topic 1 is error analysis, that I'll put more emphasis on, and because the first, and then the more specific one would be pressure, and more specifically due to having camps in their demonstration. And topic 2 would be initial conditions and critical value. And our third topic, if we have time, will be the experimental procedure and on how they measured the oscillations. Because that one was also really not as clear as the other presentations. And that's it, and I'm open to discussion.
Okay, so that's now discussion time.
Okay, so let's move on to some errors. What are some assumptions that you made on your experiments? Because I don't think we really talked about
question, but so maybe I go back to my setup. So first of all, I have a in the bucket. So basically, I see you talking about pressure. So are you talking about pressure of the bottle? Water is a bottle.
Yeah.
Yeah. So basically, the pressure is ultimately will affect the flow rate, because I care about flow rate ultimately. So the pressure wouldn't be. It's like considered in the total flow rate, like is it an outcome, like is it a factor that affects my flow rate, and I get my flow rate as a result, so I don't see where.
So you did account for the pressure?
Yeah, because the pressure will ultimately affect the water flow rate. So.
Okay, what pressure are we talking about here? The pressure I'm talking about is, okay, first question, do you have a cap on that water bucket? Because by the looks of it,
it's that one.
Okay.
It might not be played very fun.
Okay. Okay, that doesn't really matter. And okay, if the water level were to drop, wouldn't there be an decreasing pressure as the water levels drop, because the air inside would okay.
Okay. So I can explain this by the flow rate. So we calculate the error between average flow rate and instantaneous flow rate. So I only observed about 0.6% of error. So I think what you have stated is negligible. So I didn't put it in.
0.3% of error.
0.3% of error. Yeah.
Okay. to what extent do you think that will not affect the overall experiment? Because as you said, chaos, like in chaos, the initial conditions matter extremely much.
Yeah,
Okay. What is your definition of being negligible in terms of like a chaos experiment?
But I personally suggest that that is like what you have stated are all ultimately what affects my flow rates, and I observed the flow rates as my experiment, so it doesn't happen after the dropping condition. It's before the water pours out, so it is like affecting it before, so it's not yet to be this like. I'm stating the chaotic system, but it's not like the one that the buckets, but it's like the whole dripping situation, but it's not like the water pressure you mentioned.
Okay, then do you think there was any fluctuations in the flow rates as you did the experiments? Yeah, fluctuations in flow rates. Or okay, changes.
Changes in.
Yeah, in the flow rates as you did the experiments.
So yeah, so I cannot really have a exact value about the flow rate that before I opened it up. So basically, how I get my data is that I opened up the faucet first, and I have a phone recording at the same time, and I have it like I have the amount of water, and like I collect it in like 30 seconds. So therefore, I further calculate my water flow rate through this. So I did not know my flow rate before I opened up the faucet. So so both interval and the flow rate have to be like calculated afterward. So I did not know the flow rate before I opened it up. Like I don't open it up and I know the flow rate. It's not like that.
Oh, okay. Then how do you analyze the flow rates? Through video analysis, right? Like video, right?
Yeah.
By using a video, right?
Using a video. No, I mean, how do I calculate flow rates?
Yeah. Okay.
Yeah, this one. Like I get that wet of the water, and I divide it with the time that I experience.
Okay. I mean, like, how do you measure like the fixed period or like the net weight of the water to get the flow rates?
Yeah, I have a timer that will have like it will have a 30 seconds countdown, and once the time is due, and I will just take it away. So yeah.
Okay, so basically, you just took an average of it. Okay, let's move on to another question. Can you move on to the graph?
Graph? Oh
Yeah. What's that?
Which one?
21. Yes. How do you plot? How do you plot those data points? How do you plot them? As in, like, what did you do to account for like error, or did you just not account for it? Because I don't see any error bars on it.
We don't have error bar case. These are all real data. Like, cause as I mentioned, how I get my data is that I have an interval and flow rates, and I just fit it in. Like, it's all both the interval and the flow rates are calculated afterward, and I have this data, and I just put it on the graph. So it wouldn't have the error bar between, because it is all like individual experiments. So I just fit it up to my diagram. So it's not like I do the same experiment at the same flow rate, because as I told you, I did not know the flow rate before. So this is why that I don't have an error bar, because they are all individual experiments.
Oh, okay. Now moving on to one of the theories that you talked about. Can you go to the oscillation page, which was I believe 7 or 8? Yeah. Okay. So in our own experiments, we kind of observed some like a weird phenomenon where the water drops first, and then there was a secondary drop after the drop.
Secondary drop,
like secondary drop as in like not due to like the flow rate or anything about like your entire theory, but like more like an experimental error, like the surface tension breaks off as they oscillate.
So you mean like
how do you account for those kind of stuff? How do you make sure that those slight variables or like slight changes in those kind of in the dropping, the actual dropping is like counted in your actual like
so you mean like
analysis?
probably like this one, like it might have a little drop like that. Are you like talking about that one?
Yeah. Okay. How do you account for those kind of stuff in your experiments?
How do I account for that? So that doesn't that onto the Fourier calculation, that is like because the cause of it is like the unequal perturbation because by faucet like this the surface of faucet is not exactly perpendicular to the ground. So there might be a little bit like perturbation and it's not balanced now. Like it might be the perturbation or the force direction will be a little slightly. It's not like parallel to the ground, so it will have caused the small disturbance like that one.
Wait, so you mentioned that the nozzle isn't like perpendicular.
Like you cannot ensure that it's exactly like perpendicular to the ground. So there still should be some little perturbation or some like disturbance. But I think that it's still we have calculated the error for it. So like for the little drops. So ultimately the error will be around like 0.3%. So it's still small. So we neglect.
Okay. You said that the nozzle might not be perpendicular to the ground, but then did you account like for any other errors that might cause? Because your entire experiment is based on the precondition that the nozzle is actually perpendicular, and the only downward force, the upward force is the viscosity pulling back, and the only downward force is the gravitational pull.
Yeah,
But then,
so
if it's not perpendicular to the ground, wouldn't there also be some other forces?
yeah, just like as I mentioned, that there might be some, as the water drops, so there might be some force that will go like this direction, like maybe I need to do it on it. So this is my faucets. But as when it's dropping, and the trolley will be the force like pushing back, and it will not be exactly perpendicular to the ground, so it will have a slightly angle about here, so it will cause the perturbation as I mentioned earlier. So you might observe a little bit of like this kind of shape. And we do our experiment for really like neuroscience, and I think this is like because we cannot really make it perpendicular to the ground. So this is like an inevitable we saw on our experiments, but we do calculate this error, and it only accounts for like 0.3%. So we still think it's negligible. So we didn't put it in just not too confusing.
Okay. So let's move on to your first experiments back again. Yes. My first question, did you do any errors in this, or was that just like pure observation? Did you calculate any did you calculate anything for like the different patterns of this?
Yeah, it's like it's only observation because this is the video and high-speed camera, so it is like 850 frames. So we check out every instant before dropping, and we screenshot it and we put it up it. So this is just part of it. We have like hundreds of data that we have, and we all observe a similar shape, so that I said it that it will be kind of like the same.
Okay. And okay, can you move on to your discussion?
This one, which one? I have to. Yeah. And then.
Okay. For this, for the bifurcation curves, you.
Okay, let's start. It's time for Coleman to summarize your discussion.
Okay, this is going to be like a short summary. Topic 1, error analysis. Okay, so first of all, for the error analysis parts, they don't account for pressure in the experiments as they claim it's negligible. They say that the results in a 0.6% error or something, but they themselves state that initial conditions change everything, and chaos should not be predictable where you get 0.6% of error. to about initial conditions. They lack control experiments, varying initial conditions. Topic 3, experimental procedure. They have a very vague explanation on combines average flow rate with instantaneous flow rate. And so for flow rate measurement, they have an accurate flow rate measurement as they achieve that all properties that
Okay, now it's time for a reviewer to raise questions to both reporter and the opponent.
I want to ask the report that how you control your temperature.
Well, basically, we in our lab we have air conditioning, so and we have a temperature showing right.
Okay, but we think that although you are in the air condition, but the temperature is not always constant. So could you assure that the temperature is constant? Because you say in a chaotic pattern situation have high sensitivity to initial condition.
Yeah, so I have a temperature showing like I have like real-time temperature showing right before right in our lab. So in throughout my whole experiment, the data the value on the temperature it doesn't change, but it still might be like really minor change. So I think it's like really minor, so we didn't put it into consideration.
Okay, I got it. And can you explain the reason that why the radius droplet will happen more possibility in high flow rate?
Sorry?
Can you explain the reason that why the radius droplet will happen more possibly in high flow rates?
Radius droplets.
Yeah, because you mentioned your radius.
What do you mean by radius droplets?
Can you back? Yeah, and next.
Next.
Back.
Huh?
Back. Here.
Yeah.
You say it will have the radius droplet at the high flow rate, so why the reason?
No, I mean I say that this is not fulfill the faucet condition as the statement stated, because you can see clearly that the water did not fill the whole faucet. So it's not really like a faucet that is dripping. It's more like just a fluid flowing around. So it's not the same as when, and it doesn't control at the middle of the faucets. So it's basically not dripping.
Okay, got it. And how do you certain the data of your chaotic price is not error bar but is chaos?
Wait, is it mean this one?
Yes. And you say that it's very irregular of your data, but did you consider it will be error but that's the chaos?
Yeah, so basically we use high-speed camera, so we check the time interval, and we do it like a single flow rate. We will have tracker like over hundreds of interval, and we will have this interval because one of the definition of chaotic system, it will be it will still be a closed yeah. So it's a.
Okay, I get
Okay,
it.
time's up.
Okay.
It's time for the reviewer to prepare. for the reviewer to take the floor.
Reviewer from variable 2. So this is the report's main points. The interesting driven pattern and the time interval. And the theory is the shape of the droplet and the motion after droplet close. And the chaotic behavior and the neighbor drop equation. And the experiments they mention the retractor and it will divide into the stable pattern and the bifurcation pattern and the chaotic pattern. And the experiments, the faucets readers determination. Patterns tend to be the same at low flow rates, and the pattern tends to be different high flow rates. Affect the next drop chaos. And the discussion they mentioned the double drift and the periodic race. Okay, here's the reporter strength. And they have the complete theory and the layers key points. And consistent reports and clearly mark the boundaries between phrases. But their weakness is no error bar and unclear graph and focus on the chart more and connect the formula with the experiments. And here's opponent's strength. They have precise question and good analysis, but their weakness is to speak clearly and to speak louder and can dig the theory deeper. Okay, here's the reviewer's suggestion. We think that they should control temperature more accurately and should consider the error and can consider more analytical condition. And here's their opponent and the reporter's discussion. And the opponent asks what level influence pressure, and the reporter said it's only 3% for error up here. But we think that it's possible to be very big because in chaotic risk the system will be sensitive to analytical conditions, so they can't be accurate. And next, the opponent asked changes in the flow rates, and the reporter answered it divide the next width with the time period. But we think that the timer is not accurate enough for measuring the flow rates. And the opponent asked, did you calculate error? And the report say no need to do so, so they are able to do experiments. And we think they should consider errors for and the discussion of the reviewer and the opponent. We ask the error is we ask the error for the temperature, and the opponent says it really small error. So we think that it is still cause fluctuation in the temperature. And the opponent says we have high accuracy, but we think how do they sure it's accurate enough? So the main question of the reporter is that they don't have the enough accurate for their experiments, because in chaotic parts the data of the system is very high sensitive to the initial condition. So we think that they can do more about this thing. And thank you for this is my review.
Okay, so now is the time for the reporter to conclude. 2 minutes, up to 2 minutes. Reviewer.
Okay, so hi, I'm the reporter, so I'm about to conclude my report. So in the linear system, we can observe bifurcation, but since the whole system could bifurcate, because in the so it could be in the periodic, double drift, and chaotic, like because in the linear system, the whole system could bifurcate to a certain point, so there could be more visibility. So there's still periodic in the linear system, if you do notice earlier. And since, so it is because that the whole system could bifurcate. And about the perturbation that I mentioned earlier about here, so since the faucet is not like 100% perpendicular to the ground, so there might be still some forces that, but it will just only cause minor factor to my ultimate results. And we do consider pressure in my voids as one of the factors. And like I stated, it will just ultimately affect the voids. And about the error that both opponent and reviewer mentioned of my data. So about the error that I'm not having, because every dot you see is a single experiment. So it wouldn't be error because it's not carried out in a like stand kind of condition. So you wouldn't have an error to present this. So every dot is a singular experiment. And temperature in our lab is firmly controlled because we have a real-time thermometer on the wall. So throughout all my experiments, I could assure that there is not a considerable temperature change that will bring about to any of my results. And this is my conclusion. Thank you.
All right. Finally, it's time for Drew to ask a question.
So first question to the opponent, you think that pressure is important. Can you give us what's your reason, or can you explain more?
Oh, it's because when the water level drops, I personally think that the pressure of the air exerted on the water is going to change, and that's going to push the water down, and that's going to change the flow rates.
So reviewer, you mentioned about if the deviation is coming from the arrow or is coming from the chaotic effect. So do you think it's possible to tell the difference or to judge it? Or
because the reporter did this discussion about discuss the error, so we think that his data will have the possibility it will be the error, but so we think that in this example it can see the phrase from the regular to the irregular phrase.
so for the reporter, I have two questions. One is that you mentioned about balance damping oscillation. What do you mean by balance?
Like, okay, so I have the gram in my here. So basically, the oscillation goes like this, and the amplitude will gradually will decline, and it will reach equilibrium, just like it could start vibrating. So it will ultimately reach an equilibrium. So there will be a balance movement.
So do you think that this oscillation is strongly correlated to the chaotic condition or the critical value of the flow rate?
So how does damping oscillation affect
Do you think they have correlation?
correlate to the chaotic?
Yeah.
I think so.
You have a critical value flow
Yeah,
rate,
so
right?
so when the interval is smaller than the oscillation, so the oscillation period. So the oscillation period is not. So oscillation is yet to reach its equilibrium. So it could bring about
Thank
the
you. So following the question to the reviewer, that can you explain or tell us that you can really tell if the deviation should indicate is coming from chaotic or just error bar? Yeah. Yeah.
Oh, for me. Oh, yeah.
Can you are you sure that this is coming from chaotic or might be coming from your error?
So as I stated, so I use high-speed camera to capture my video, and I collect the interval like over like over 100 and like in one single experiment. So I can assure that all the intervals are shown in this data, and it will. And this is like chaotic definition. It could go like, it will be the whole system. It will be those intervals, like these numbers, and it will go like back and forth. So this is how I show
So
that it's
you
not.
believe your time resolution is enough to resolve?
Yeah.
Yeah, so
The question for all. What are the causes of nonlinear? You say nonlinear. What physical quantities causes this nonlinear? Just say
Oh,
not a question.
So nonlinear. So based on at both.
What physical quantity? Just give the physical quantity.
So we focus on the step preventive solution. So when it is not equal to 0, the system will be non-linear.
So what physical quantities?
Oh,
You mean
physical.
velocity or pressure or anything?
So I shared. Let me show you. So I have it back here.
Just say what is the physical quantity.
So I think there's homogeneity and like superposition will affect to determine the system is linear or nonlinear, so whether it's linear or nonlinear. So and if it fulfills the homogeneity, as I mentioned, the perturbation effects in chaotic will be like it would not be enlarged in the same kind of degree, but in periodic. But if it is linear, it will be in the same degree.
I just want some physical quantities.
Yeah. Oh, sorry. I mean, I use like the velocity to ensure.
Okay, just that.
Wait, okay. So
What physical quantity causes nonlinear?
viscosity, gravity, and yeah, that's probably a surface tension. Is that kind of the answer you're looking for?
Okay, just
We think is the surface tension and the physical force because we think that at the
no listen. Just give.
we think that at the regular pattern, the surface tension and the gravity will have the main effect in the condition, but in the irregular phase, the surface tension will have the minor effect, and the physical force will have a big effect in this situation. So we think it's these 3 factors.
Right. Right, so it's time for the reporter. So 6, 7, 7, 6, and 6. Now for the opponent. 6, 8, 7, 5, 5. Now for reviewer. Yeah, all 6. Okay, thank you everyone. So let's take 几分钟，休息15分钟。